Welcome to this lecture. This is the first lecture of week 2. In this week, we are going to connect lower dimensional measures with higher dimensional measures, and using this connection, we are also going to be talking about independence of random variables. Without further delay, let's move on to the slides. Let's recall these very basic facts that a real valued random variable, as we understand it, is a real valued measurable function defined on some probability space. Now, given any such random variable, we can construct a Borel probability measure on the real line. It simply means that the measure is defined on the real line together with the Borel sigma field. Now, this measure that we construct, this is called the law or distribution of the random variable. We can do the opposite construction also, that given any probability measure on the real line, of course again defined on the Borel sigma field, we can construct an explicit random variable with this given measure as its law. Now, a priori it is not clear whether the random variable that we construct will be possible to construct it on a very specified probability space. What we typically do is that we leave the choice of the domain space, the domain probability space, to be free, and then we focus mostly on the law. As it so happens, given a random variable, if we know its law, then immediately all the important properties about the random variable can be extracted from this law itself, and therefore we will not focus too much on the domain probability space. Now, let us bring in the case of two random variables. If we start with two given probability measures again on the real line, call them mu and nu, then we can construct by this previous construction random variables, let us call them x and y, with mu and nu as their law respectively. However, in this construction it is not clear a priori if these random variables are getting defined on the same probability space. It might be a priori that these probability spaces are different. Now, we can ask the question whether we can construct them on the same probability space or not. More generally, we are actually going to require multiple random variables, all of which has to be defined on the same probability space, and these multiple random variables, a special case of that will be sequences of random variables, and we would like to talk about their convergences and all those. Therefore, we require all of these random variables with specified law to be defined on the same probability space, so that we can talk about convergences and other analytical properties. In what follows, what we are going to discuss is construction related to this specific issue, but this will require certain measure theoretic techniques. So, in the first few lectures, we are going to concentrate on measure theoretic preliminaries, which will help us talk about these properties. First, we recall the situation what is happening on the real line. Consider this class which we denote by script C. This is the class of all finite disjoint union of left open and right closed intervals like this. Here we only consider all these intervals in the real line, and recall that this collection, which is this finite disjoint unions of these intervals, forms a field of subsets of the real line, and moreover it also generates the Borel sigma field. We typically denote this fact by saying sigma of C, which is the minimal sigma field generated by script C, is the Borel sigma field. We write this equality. Now, once you have this generating class which turns out to be a field in this case, we can apply the Characterity extension theorem, and recall that Characterity extension theorem tells us that any sigma finite measure on this measure space is determined by its values on this field, and therefore, if we concentrate on the example of the Lebesgue measure for example, then it is determined by its values on this collection of finite disjoint union of intervals. But again, using the properties of measures, it is enough to know the values on these specified intervals only, and therefore, the Lebesgue measure gets determined by this property, which essentially tells you that Lebesgue measure is the usual length function for intervals. And exact situation appears in the higher dimension also. Let us look at the 2-dimensional case. Consider the class which we now denote by C superscript 2 of all finite disjoint union of rectangles now of the form open A closed B cross open C closed D, and these rectangles are considered inside R2. So, we vary A, B and C, D as appropriate and obtain this class of rectangles and then consider finite disjoint unions of them. Recall again that this class of sets is a field of subsets of R2, and as pointed out in the 1-dimensional case, it will again generate the Borel sigma field which we call as B of R2, and we write this to denote this fact that the sigma field generated by this class of sets is the Borel sigma field. But since this class C2 itself is a field, again we appeal to the Characterity extension theorem, and then we claim that any sigma finite measure on this measurable space is determined by its values on this field. In particular, we focus on individual rectangles, and all we have to look at is the area formula, that the area is exactly what is getting assigned by the Lebesgue measure in 2 dimensions. So, this is the usual area function. But now, let us connect the 1-dimensional and the 2-dimensional Lebesgue measures. The area of a rectangle, as we understand, is the product of the length of the sides, and therefore, we can write this relation about the Lebesgue measures in 1 and 2 dimensions, that the Lebesgue measure of the rectangle, which is the area, it is exactly the product of the length of the sides which is given by the usual Lebesgue measure in 1 dimension, and this is true for all possible rectangles that we see in R2. And this is the relation that is now also defined on the generating class of sets. You can extend this ideas, and therefore, motivated by this, what we are going to talk about is trying to link this 1-dimensional measures to higher dimensional measures, or even lower dimensional measures to higher dimensional measures. So, this idea will be using information from measures on lower dimensional spaces, and we are going to construct such measures on higher dimensions. To start off with this construction, let us set up certain basic notations. What we start off with are 2 given measure spaces, omega 1 f1 mu 1, omega 2 f2 mu 2. Now, given these 2 measure spaces, what we are going to do is to construct a measure on this product space, omega 1 cross omega 2. This is the usual Cartesian product of the sets. You can compare it with the earlier example that we considered, which is the case of R2, which should be identified with R cross R. So, this is a pair of real numbers. Now, our first step in this procedure will be to identify an appropriate sigma field on this product set. So, to do this, we consider the situation as we have seen in the case of the Borel sigma fields. We start off with the Cartesian product, which is of this form, that we take a set A from the first collection and a set B from the second collection. So, this collection script f1 and script f2 are given to be sigma fields. Now, we look at all such Cartesian products and their collections. In general, as it happens that this Cartesian product of these collections is not a sigma field. As an exercise to you, you can check that Borel sigma field on the real line product with itself does not form a sigma field. But then what we can do is that you consider this collection of product type sets and consider the sigma field generated by this collection. We shall refer to this sigma field as the product sigma field on the product set omega 1 cross omega 2. So, therefore, we are first of all collecting all the product type sets and then generating the sigma field. So, we will get some extra sets. So, the whole collection that we end up having, that is what we are going to call as the product sigma field on the product set omega 1 cross omega 2. Now, to talk about it, we are going to use this notation using the tensor notation, and we are going to read it as f1 tensor f2. f1 tensor f2, as we have just defined, is the sigma field generated by the product of the collections f1 cross f2. Now, in some textbooks there is certain ambiguity about these notations. So, let us make that clear. The notation F1 cross F2, which we used for the Cartesian product, in some textbook that has also been used for the sigma field itself. But we want to avoid any confusion, and we will use this tensor product notation throughout to denote the product sigma field. So, this will distinguish it from the usual Cartesian product, which is F1 cross F2. So, whenever you are referring to any textbook, please first check the notational convention used in that book, so that you do not get into any confusion. Now, using this new product sigma field idea that we have just introduced, let us go back to the case of real line and R2. Start with any A cross B, a product type set in BR cross BR. Then, as it so happens, by the definition itself, each of these sets must be coming from the Borel sigma field on the real line, and we can immediately check that the product type set, which is A cross B, actually forms a Borel measurable set in R2, and therefore, it is in the collection Borel sigma field on R2. Consequently, what we have obtained is the Cartesian product of BR cross BR is contained in the Borel sigma field on R2. But let us try to use the fact that Borel sigma field on R2 by definition is a sigma field, and therefore, it will contain the minimal sigma field generated by these product type sets. And therefore, the product sigma field that we have just defined is contained in the Borel sigma field of R2. We now show the other side of the inclusion, and thereby we will obtain the equality. We note first that the Borel sigma field on R2 is generated by these rectangular sets, right, where we are varying the parameters A, B and C, D like this. And now, what we observe is first is that this product type set by definition is in the Cartesian product of the Borel sigma field with itself, and hence the Borel sigma field on R2 by definition it is generated by these collections, but then it is also therefore contained in the sigma field generated by the Cartesian product of Borel sigma field with on R with itself, and therefore, this is exactly the product sigma field that we have just introduced. So, therefore, we have the other side of the inclusion. So, together with these both inclusions, what we end up having is that the Borel sigma field on R2 is the Cartesian product of Borel sigma field on R with itself. We can generalize these constructions, and some further properties are listed as exercises. Please try them out. Let us consider three measurable spaces which we write as omega j fj. But now we can talk about the Cartesian product of sets, which is omega 1 cross omega 2 cross omega 3, and we can ask, can we construct a product sigma field on this set? Here you can see that first we can perform the product operation on F2 and F3, and then obtained sigma field we can do again a product operation with F1. So, therefore, we will have a sigma field on this product set, which is omega 1 cross omega 2 cross omega 3. But we could do it the other way also. We could first perform the product operation on F1 and F2, and then the resultant sigma field can be taken product with the F3. In either case, what we will have is an associativity property that these two sigma fields that we have constructed, they will coincide. So, this is the exercise, please check it. Now, in the setting of our earlier exercise, we are going to denote this common sigma field as F1 cross F2 cross F3. We will not put any bracket because we have just understood that it is either way we can perform the operations and we will obtain the same sigma field. Now, in this setting we have further properties involving the Borel sigma fields on general Euclidean spaces. Let us look at the Borel sigma field on the m dimensional space and the n dimensional space. If you take the product of these two sigma fields, the product sigma field that you will have will be a sigma field on R m plus m dimensional Euclidean space. Now, you can compare it with the usual sigma field, the Borel sigma field on the m plus 1 dimensional space, and you can again show the equality. The proof again follows the similar argument that we performed for the 1 plus 1 equal to 2 dimensional case. We can also look at the associativity property and identify the structural properties of the n dimensional Borel sigma field as the n-fold product of the one dimensional Borel sigma fields. Please work this out. We now are going to discuss a very useful result which will be used in the further lectures. We start with two measurable spaces omega 1 f1 and omega 2 f2. Here what we do first is that we first fix a point in the first set omega 1 and consider this function defined as pi subscript x. This pi subscript x is a function defined on omega 2 and takes it into the Cartesian product of the sets. So, the way it is defined is that any point y in omega 2 is taken into this pair x comma y. Here the function is essentially getting parameterized by the point small x that we have chosen from the first set. And the claim is that this function is f2 over f1 tensor f2 measurable, meaning this is a measurable function with the measurable space on the domain side being omega 2 f2 and on the range side it is omega 1 cross omega 2 together with the product sigma field. So, therefore, we have this measurability of this function. We are going to state another relevant result by looking at the other component. Here again, if you choose a point from the second set, you can define a similar function. Just to distinguish it from the first function, we write this one in the superscript. So, whenever we are using the parameterization from the first set, we will write the subscript. Whenever we are writing the parameterization with the second set, then we will write it in the superscript. Here what we are saying is that you fix a point in the second set and then look at this function which is defined on omega 1 and takes it into the Cartesian product of the sets omega 1 cross omega 2 by sending arbitrary point small x to the pair x comma y. Now again, similar to the case earlier, we will have that this function is f1 over f1 tensor f2 measurable. Here there is a minor typo in the lecture notes, it will be corrected in the final lecture notes supplied to you. So again, this pi superscript y function is a measurable function with the domain side measurable space given by omega 1 f1 and the range side measurable space given by omega 1 cross omega 2 together with the product sigma field. Now the proof for the these results are similar and we only prove for the first case. We start by looking at sets of the form A cross B, where A is coming from the first sigma field and B is coming from the second sigma field. But as per our definition, these product type sets generate the product sigma field. Therefore, to check the measurability of this function which we defined as pi subscript x, it is enough to check that the pre-images of this product type sets is belonging to the domain side sigma field which is f2. If we verify this for this class of generating sets, then we will be done and we will have the measurability. So, let us verify the pre-images for this product type sets. Observe that if your point small x which is coming from the first set, it is inside the set capital A, then the pre-image can be identified as the set B. Otherwise, when the point small x is not in A, then this pre-image actually turns out to be empty set. This is a very easy verification, please check this. But then our assumption is that the sets A is in F1, B is in F2, therefore, the pre-images that we consider now must be in F2, and hence what we have verified is that pre-images for generating sets is coming in the domain side sigma field, and therefore, this implies the measurability property of the function pi subscript x, and the result follows. So, the proof for pi superscript y is similar. Now, we stop here and we are going to use this result in the next lecture to finally construct the measures in higher dimensions, meaning on omega 1 cross omega 2 using the given measures mu1 and mu2. We stop here, see you next time, thank you.